talk. Before I start, I want to make a quick note, because Martin, your presentation really resonated well with me. I think it shows us how far there still is to go. Right? While the complexity is exciting in science, it's also a hurdle for clinical translation. It remains open, it drives open questions, and regulators don't like too many questions. And so thank you very much for that talk. I think it really is important for us to spend a lot of time understanding these questions, specifically because of their complexity within specific disease states. I think a challenge will remain to still show what about the mitochondria's function is truly therapeutically efficacious. We're talking about vital respiration of the mitochondria, but what is it? Does it correlate? Is the causality? And I think spending a lot of time there is certainly something that the scientific community needs to drive. We as a company don't have the means to. But at the end of the day, this is where I believe the biggest impact derives from understanding truly what do the mitochondria do and where are they therefore efficacious. At Cellevie, we're trying to leverage mitochondria specifically for IRI. We're building on Jim's phenomenal work on showing how they can ameliorate the damage arising from ischemia and the subsequent reperfusion. A topic that has been addressed in the previous talks a lot is autologous versus allogeneic. I have a pretty bold answer to this. I don't think that we can build a therapy on an autologous product that will be broadly available and commercially viable. I think every thought of us should move quickly and as quickly as possible towards a scalable product that is allogeneic, that is centrally manufactured, that is controlled. And the most simple of the reasons is if you manufacture therapy in a hospital, it doesn't mean that you're not subject to the same requirements on batch release, on quality controls. In Europe, on release by what is called a qualified person, that needs to be there for every single manufacturing that you do. It's becoming cumbersome, it's becoming prohibitively expensive. And the reality is that while investors and pharma companies do care about patients, and I don't want to hear anything different, but they will select their horses based on what will also generate a return. And unfortunately, autologous mitochondrial transplantation, I doubt, will be that horse. Indeed, we tried to raise funding based on autologous mitochondrial transplantation for 2 years straight, with very, very little success. And this with Jim on the board, with clinical data available. Right? Investors want to see how can you make this a true clinical success, a commercial success, unfortunately, as well. So we've been working a lot on allogeneic mitochondria, developing a product that's workable from tissue, workable from cell line, and so that indeed has been a big effort at Cellevie, and one that we hope will be fruitious. Because at the end of the day, yes, this looks good in our animal models, but the patient is the true testament. While we were working on our product, we've also been expanding the pipeline. Instead of specifically extending towards diseases, one reason is the complexity that we believe is inherent within every disease and how the mitochondria relate to it. We've been more focused on how can we leverage mitochondria more broadly as a platform. Specifically, and most actually advanced is our work on mitochondria as gene therapy carriers. We showed we can load mitochondria, mRNA, DNA, siRNA, and see that payload arrive in cells, be transcribed, and therefore have a potentially dual, maybe even synergistic effect. Our work in IRI is, I think, the one that's most well known, and it's building upon Jim's work, and that we have been taking, staying in the area of ischemia-reperfusion injury. We've been tweaking it a little bit. Tweaking it again out of commercial considerations. At the end of the day, what counts is clinical data. The therapy, the approach lives and dies with clinical data. Right? That was true for antibody drug conjugates, that was true for T-cell therapy. I mean, before you see it in the clinic, I don't think the field is really taking off, right? Because there's too much reluctance to truly put a lot of economic power behind it. And so we look at the field of IRI in the sense of where is the quickest and cheapest path to clinical translation. And if you go to any IRI indication and look at clinically relevant endpoints, their incidence, their variation, and the expectation of your therapy to affect those endpoints, you end up in kidney transplantation, giving you the most likely chance to see a clinically relevant, meaning statistically meaningful effect in the patient population that counts in the low hundreds rather than thousands. So here we are working on kidney transplantation as our first indication. We've been testing mitochondria actually also in an ex vivo model and seeing the same similar results that you've shown. We've also put them into an acute ischemia setting in the pig, so in vivo model. We occluded both renal arteries for 90 minutes straight. We then reperfused and give mitochondria during the reperfusion, and then we followed these animals out for 4 days. And the data looks pretty compelling. If we look at the reduction in injury, we see creatinine and BUN both increase when the kidney is damaged in the blood till the kidney recovers, but it's a clear indicator of kidney injury. And here we see that we can reduce those kidney damage markers by more than 50%. And if we look into the pathology, we also see this nicely reflected. The necrotic area in the control group is around 5, a little more percent, whereas with 0.5% in the treated kidneys. And here I want to take a short detour, which is how does mitochondrial transplantation actually work? Okay. And I think the mechanism of action is still not fully understood, but one that has been postulated now frequently is that of mitophagy and mitogenesis. And that, we believe at least, can be seen potentially here if you think about its effect on the ischemic and reperfusion cascade, which is keeping cells that would otherwise die from dying. And now, if indeed mitophagy and mitogenesis were at play with the ischemic reperfusion injuries, ability of mitochondria to treat, well, shouldn't we see more mitochondria, not human, not the ones that we use, but more endogenous mitochondria of the animals we treat in those organs that we treated? So we did a dose-response study in mice, basically the same model, acute ischemic occlusion followed by reperfusion and a 1-week follow-up, seeing a nice dose-response in the pathology as indicated by scores of damage in cortex and medulla. Interestingly, we also see less inflammation. Now, since I'm running out of time, what did the endogenous mouse mitochondrial DNA content do? On the right-hand side, we didn't specifically investigate this, we observed this. I want to caution this a bit. But what we did observe is that in those groups where the dose was therapeutically efficacious, we also saw elevated levels of endogenous mouse mitochondrial DNA, suggesting more mitochondrial mass in those cells and therefore potentially higher mitogenesis. May also be due to other reasons, but at least we see some support here, and I wanted to share these insights with you. And if you are interested in learning how mitochondria may actually bring gene therapy to organs, happy to chat. We've shown this in mice, we've shown this in pigs. And if there are any questions, please let me know.
Thanks so much. Open the floor to questions. Again, first learning patients, patient representatives, and questions.
Zucker, University of California, Irvine. It was very interesting you said that as a mechanism, mitophagy and mitogenesis related. Mitophagy is activated by depolarized mitochondria, mostly dysfunctional mitochondria. So I was wondering whether actually you had done any experiment using depolarized or damaged mitochondria doing a similar, giving rise to similar results like active mitochondria?
Good question. Going back to my point earlier, as a commercial effort, we have very limited resources to investigate truly mechanistic questions. So the short answer is no. There was a publication last year, however, suggesting that mitochondria missing PINK1, which was postulated to activate the cascade of autophagy followed potentially by mitogenesis, does not lead to the same, at least downstream effects. So to be fair, I don't know the answer. There's some evidence that might be in line with what you just postulated, but we haven't looked at it ourselves.
I see another question.
Thank you. Do you see any evidence that the source of mitochondria actually makes a difference?
No. We've tested this with different cell lines, different tissues, and at least within the ischemia-reperfusion injury context. Again, I think we need to be careful not to extrapolate too far and beyond within the context that we have tested. But I think it's fair to say that the source question has reproducibly not shown to make a difference. Where we have seen a difference is how mitochondria react to storing based on source. So there's sources that lend themselves better to storing than others.
What do you think is the chance that the effect of the active ingredient in mitochondrial transplantation is ATP versus something else?
I think Jim published some work showing that just ATP didn't make a difference. That ATP has an impact, we do believe. Whether that's from ATP production that's triggered, or whether that's from ATP brought in by the mitochondria, I wouldn't know. But if we look at how we some of the work, let me leave it at this. I think it's going to be otherwise too much detail. But yes, we believe ATP do matter, but how it matters, we don't exactly know.
And as a final question, I'll just pose one if I may. How do you imagine ways to allopate differentiation as we try to move towards standardized, ready to go, market-ready mitochondria for clinicians or any therapeutic?
The haplotype question, interestingly, has come up a few times. And I think I'm more on the dismissive end of that spectrum with my answer. But to be honest, we don't have enough data to tell one thing or the other. I want to put out there that the results you saw in mice and pigs were from human mitochondria, right? So I think haplotypes versus xenospecies differences are probably less in the haplotype sense than in the species sense. And also, if we believe, which we frankly do, is that the mitochondria act as a catalyst rather than as a catalyst to the mitochondrial system inside of the cell, and reinvigorating that cell energy metabolism. We don't need, so to speak, I don't believe we need a match, but that remains to be seen more research.
Wonderful. Thank you so much.
No, thank you.